Okay. So I wanted to show you a software tool called, and it's the generic name is TCAD, which is technical CAD, but really what it is software that you can give it a recipe to make transistors, and it will actually virtually simulate that, and then it'll virtually simulate what you just made. And we have Synopsys TCAD, and Professor Hugh Wong worked at Synopsys for 6 years, and actually he does have his own research group with undergrads, and they're able to do these simulations, and you can do them remotely. Now, the reason why I wanted to show it to you just a little bit, but I have to pause the recording because the license, let's just say due to licensing, they don't want me publishing how to use the tool in public, okay? So I'm sorry if you're watching this video, but I do have tutorials and things, and if you're into it, or I can even do a repeat of this. So we're going to resume recording. So we had a MOS CV capacitor that we simulate in TCAD, and then we can actually measure it with our resources in the MPL, which now I'm just going to give you a rough overview of the capabilities of that lab. So these pictures were more, they're not technical pictures, and those are actually my children when they were young. That was a former student, and we're just taking a picture of a wafer. There's the solar cell test setup. And you can load this testing software right on a laptop, and then you can automatically test your solar cells. This is a source measurement unit where it can measure current and voltage accurately at the same time. But also this whole thing can measure the MOS CV that we just simulated it. And actually, I think it's in the same spot. Now, yeah, I was trying to show how we affected students, and so I've got a lot of pictures of students. Now, this is one of the first ICs that was designed at San Jose State. We had it fabricated somewhere else, and I think we're about to be able to do that again. I've been looking, so that's a whole other research area, right? But the students went and designed, all the transistors in here. You connect them up. Somebody else makes it. It comes back, and we test it. Now this is the furnace where we heat things up, and we can get the dopants and grow oxide. Now we just won a $600,000 grant to buy a new one. It could take 4 months to install, but the old one is still there. These are the wet chemical benches. Oops. Which we're buying new ones because this one's got a little, well, they're no longer safe. And he's now, Neil here is a big resource. He's the building safety specialist now. That's, oh, that was a chip we made actually in lab. Although I had to do some of the work at Stanford. And things got a little over etched because I hadn't worked out the process yet. But this was an interesting device where these are all like switch capacitors, and this is the impulse response of the filter. And when you send the signal through, it actually acts like a low pass filter. More wet benches. This is the former dean. again, these pictures were more for like a newsletter than scientific. But yeah, here's the wafers that we use, and you would load them in. And on Friday afternoons, I used to just bring people in and show you how to load a wafer. I'd even have you break a wafer so that you just would be comfortable, right? I have you, practice loading wafers, measuring thicknesses, things like that, that are relatively easy to teach, right? Oh, I guess that was it. Anyway, that's not really the whole MPL. We do have a website that's undergoing some changes, but yeah, these are transistors we've made. That's a ring oscillator. We don't have this machine anymore, but we do have a way to deposit metal. Now, interestingly enough, this is a transistor IV that didn't really work, but it took a good picture, so they kept it. We also have MEMS where, we're etching these thick structures into surfaces. And these are beams that would resonate. Now, these ones didn't fabricate so well, but, that's okay. Anyway, we have all these people that support it. And so that you could be, so right now, yeah, I'm working on silicon carbide. I have silicon carbide wafers. And what's great about silicon carbide is that it can dissipate a lot of heat. It's a very robust material, but its density of states, that Ni, which you might remember from 128 for silicon being 1.5 times 10 to the 10th centimeters per cubic centimeter. Well, it's a lot smaller in silicon carbide. And the thing about that number, that Ni, is it changes with temperature. It gets bigger with temperature. And if you have 10 to the 16th dopant atoms, right, it's got to be greater than Ni. And so if you raise the temperature, Ni might get bigger than your doping concentration, and then it won't work. So in order to have a diode, right, you have to have an N region and a P region. But if you raise the temperature to where your intrinsic carrier concentration is bigger than whatever dopant you put in, you'll no longer have a diode. So let's say you had a P plus N diode. At some point, you would have a P plus intrinsic diode, which isn't really a diode at all. And so BJTs, they need two diodes. MOSFETs, they need two diodes to work, right? And so if you raise the temperature on silicon, it'll just stop working. But with silicon carbide, it'll keep working. And so it's a major material system of interest for the Navy and things like that. Let's see, let's see if I can. I'm still sharing, right? You guys can still see my screen, right?
Yeah.
Okay, sorry. Almost there. I'm sorry. Okay. So one of the projects that we've been working on and we need to continue is we were modeling hafnium oxide on silicon carbide MOS devices. Now, hafnium oxide has a higher dielectric constant, so you can kind of get the same effective transistor characteristics for a thicker oxide. Now, why use a thicker oxide, you say? Well, if you make it too thin, you can have quantum mechanical tunneling through the gate and it'll leak, right? So as you scale devices smaller and smaller, you're making the oxide thickness thinner and thinner. So if you switch to hafnium oxide, you can make it effectively thinner, electrically thinner, but you can avoid the quantum mechanical tunneling. Anyway, this was a report. You can see there's our CV plot. And then we extracted some spice parameters and made a simulation of an op amp, which we did. I believe that's an LT spice, right? And there's a Bodie plot. And we talked a lot about stability in 110. And what we do is that op amps aren't inherently stable, and you have to add a resistor and a capacitor in the feedback path, right? So so that it doesn't oscillate on you. But anyway, that's that. Yeah. So I guess what I'm saying is not everything. I mean, I've been, kind of pounding on stochastic resonance, but that's not the only thing that I work on. All right. It's just I had been working on it because it's something that can be done remotely. These kind of simulations, they can be done remotely. But yeah, I'd really like to get back into the lab. So let's see. So that's just a little bit more about what I'm about. So I thought we could just go over a little bit about picking a senior project team. Now, let's see. Alex, you're ready. Ryan, are you in 198A?
I'm currently enrolled, yeah.
Okay. Gilbert, are you in 198A? No, you're taking 122, right?
Yeah.
Okay, so no, not yet. And Pranav, I forget.
Yeah, I'm with Gilbert.
Okay, so you're taking 122 this semester. All right, that's okay. So here's the thing. There, really you've got your teammates and the topic. And I guess you have your advisor. And So really, your advisor is your number one area person to help you technically, right? So if you were going to do an advanced power supply for a Mars rover, or no, advanced power supply for a Venus rover, that's even better, right? You're probably going to want Professor Badawi, right? Because he's into power supplies. However, if that project might involve some robotics, right? So maybe Professor Badawi is your number one person, but if you needed help, you could always go and ask Professor Shu, for some advice, or embedded systems, you could go back to your 120 instructor, right? But it's your primary source of technical help. And then, yeah, sometimes if there's teamwork issues that can't be resolved, the professor can be there. They can give you help on selecting your topic, refining your topic, showing you how to do a literature review, right? Because you want a project that showcases you, right? However, to start from scratch, to have some kind of fully functional product that you can sell in a year, that's not really realistic, right? So you want something that at the end, you have a really good demo that showcases what you can do, but also no one else is doing, right? So, I mean, I would get people saying they wanted to do a remote control for the TV, and which, yeah, you'd learn a lot figuring out how to remote control would work. But I mean, if you can buy it at the store, it's probably not going to be great for a senior project. Now, I have talked to some folks in industry where they'll say, do an op amp out of discrete parts. You'll learn a lot. Now, those projects are great. I think they can burnish your resume, but it's not really a senior project worthy. And then some people can go too ambitious as well. So they'll, but in order to find out whether your project is unique or not, right, you have to do a literature review. And of course, there's Google, and you might think, well, there's no product that does what I do. But again, it might not really, that might be a good start, but we need to learn how to read and investigate, technical articles, right? Because maybe your product doesn't exist, but if it's using a communication system, there's plenty of articles on that. If you have power supplies and you need to do a different one, there's plenty of journal articles on that. And so, yeah, which is circling back to the team, where you have a big project, how do you divvy up the work so that you can work in parallel and not in not serially. So let's say your senior project was you're going to do a Segway, right? Well, you're going to need some kind of mechanical frame to put all the parts in. You're going to need the control systems with sensors, and you're going to need a power system, right? Now, the thing is you might say, well, do the frame, do the power systems, and then do the control systems in that order. You're never going to finish. So how can you do the chassis in parallel with the power systems in parallel with the control systems? Now, what you can do is, let's say, wait, how can I do the control systems if I don't have the chassis? Well, you can probably make a mock-up, right, of the control systems. But wait, how can I do the control systems if I don't have the power supply? And yeah, you could just hook up a power supply. But then you might say, how can I do the power supply? How can I design that unless the sensors are done, right? And the control systems, and how much, on a Segway, you're going to have large current spikes. Well, this is now what you can do is you can create a specification that the control system yeah, we're going to estimate it's going to have this kind of current spike and it's going to need this voltage. And then with power systems, you can kind of make a fake load that will cause a current spike, that will have a certain draw, right? And if you, I mean, let's say you had a DC power supply, it's supposed to do, give you 5 volts and 5 amps, right? Well, all you need is a 1 ohm resistor, right, to do that as a load. Of course, a quarter watt resistor is not going to work, right? So these, let's see if the screen is still, I'm just gonna, where's me? So you can get power resistors and they're like, they're as big as the handle of this brush, okay? So, but, so you can work with that resistor, you know, a big power resistor on your power system to make sure that it's working. And you might say, how do I do a spiking current? Well, you hook up a MOSFET to that resistor, and and you just turn that MOSFET off and on, and now you're controlling the current through that resistor. So you're just kind of faking it, simulating it, so that you can do each part in parallel, right? So now, yeah, how do you start on the chassis until you know how big the battery packs are and things like that? Well, you have to, you know, you look up batteries and you just create a specification that this is the space you have and you're going to have to fit inside it. On the other hand, if all of a sudden you needed 1 more battery pack and the chassis couldn't handle it, that's problematic. But you might just have to say, this is our version 1, right? Where, yeah, we could use more power later. And then version 2, you put that in there, okay? So this is just like really high level kind of teammate stuff. But you want to make sure that everybody has something to contribute. The worst thing is, like, let's say, you know, not that it would be a real senior project, but you're doing a filter, right? Like your 110 lab filter for your pulse width modulated DAC, and you have 3 people doing that. Well, they're all going to do the simulation, they're all going to do this, they're all going to do that. Well, nobody will have anything to do. And so what'll happen is one person will do all the work and the other 2 won't, because there's just nothing to do. Maybe they're hard workers, but they just don't want to fight with a dominant personality. So it might be, well, 1 pulse width modulated DAC going in where one person's in charge of it, but it's going into a system that does this, and then everybody needs to be needed, okay? And so when you're divvying up the work, you can't just say, well, everybody does everything, because that'll lead to disaster. And yeah, if you have a team of 3 or higher, you will have one person who's going to have to be the leader and keep people on track, things like that. But right, they're going to grade. Now, what I found is, like Professor Shu, you know, he would meet with his students every Saturday morning, right? And it always seemed that he had some of the best senior projects, most well developed, okay? Some faculty just let you do whatever you want, and you know, you can pick the topic and they don't really care. They just kind of do the grading, maybe offer some advice. Now the thing is if the topic aligns with the professor, then you'll probably get a lot more help, okay? but with the team, I think, and unfortunately, because you haven't met face to face in a lab, you don't really know how people work well, how they work together, what their style is, right? And so usually in 122 and 120 lab, right, you'd kind of get to know people and know who you wanted to work with and who you didn't want to work with. But probably the biggest thing is the style, right? And hold on a sec, there's a chat. Oh, yep. So, um, but like, I don't know if you ever heard of a story where you there were best friends and then they moved in together and it just blew up and they couldn't stand each other living together. Because you kind of have to have rules of the road before you live together or even join a project. Like, how are we going to communicate, right? And you got to really be honest. Like, well, I if you don't respond to my text within 5 minutes, I start getting upset. That might be unreasonable, right? But to say, all right, we respond to texts this quickly, emails this quickly, and things like that. You also have to be honest with each other of how much time you have for the project. Well, how many courses are you taking? What is it? What is your workload? What is going on in the family, right? And if you have something ambitious, right, you just, whatever you say you're going to do, you have to do it, right? And so senior project is very self-directed, but it is like a lot of work that, you know, it's not like there's this exam, right, that is coming. The project has to work and it's coming, but the deadline is really pushed out, right? It's a whole year, right? And so then then the other thing is like, when do you like to get things done? So let's take a deadline, right? Let's say the deadline is next Saturday, right? Some people, right, if I say the deadline is on Saturday, as soon as this Zoom call is over, they want to get it done. And some people are like, oh, if the deadline is Saturday, I will get it done at, whatever the due date is, 8 o'clock on Saturday, right? And yeah, they'll build in fudge time if something goes wrong, but they don't get it done early. They get it done exactly on time. Now, that can drive people crazy, right? Now, sometimes people aren't working on it, or they like to work in this bursty, intuitive way that, that's okay as long as you're getting your things done. But the worst thing is to just not keep the team apprised of what you're doing. You might say, I'm working on it. What do I got to tell anybody about it? Of course I get my things done. But that kind of communication of our things going on, and not making people have to guess, am I doing the work? Am I not doing the work? Now, here's the thing, getting things done early or starting on them early, I don't know how you can survive in engineering for very long without adopting them. Maybe as a freshman, people start off one way, but they certainly learn their lessons not to leave things for the last moment. Now, yeah, when you're working with artists and things like that, they're like, we're going to stay up all night and do this piece of art. Well, maybe that works for them, but in engineering, that's a recipe for disaster, right? Slow and steady. Now, even grades are supposed to be a secret, but of course, I think everybody thinks they know how everybody else is doing. But unless you read their transcripts, right, you don't really know, right? Somebody could be under or overestimating their grades. Grades are important, but it's not the whole story. Okay. So, I know faculty, they only want to take above a certain GPA. there was times where I didn't want to take over a certain GPA, right? Because some people, they're very so grade oriented, right? That they won't really work on the project as much as they will on an exam, right? And so sometimes people with A's can be a bit selfish, right? Sometimes people with lower grades, they just don't have the time to dedicate to their studies, right? And what I found is you have no idea. For just looking at somebody's grade, you don't really know the person, okay? It's a thing, it's important for sure, right? And yeah, there's companies, if you have above a 3.0, you're allowed to apply. If you're above a 3, you're allowed to apply. But it's not, it's a number, okay? But you don't know why that number is the way it is, okay? But so, there are varying skill levels that you'll have. Some people know things a lot better. Maybe they have more experience. Maybe they're able to really dig into it. And so, yeah, sometimes I've had teams where both people were kind of weak, but they worked really well together. And by the end of senior project, I would say they're strong, right? And so what I'm saying is if there was like an algorithm or something for designing the perfect team, and you knew what that algorithm was, you'd be very rich, right? You're trying to predict human behavior, all right? But I think, like, if you're now trying to figure out your senior project before classes even started, right, that's great, right? Some people, they wait until class starts, and that's okay as well. But that working style thing of bursty versus slow and steady. And what I found is, like, yeah, students who are older or have more experience, they tend on, or have family, they tend to be more on the slow and steady. And if you're kind of just only have to worry about yourself, well, they tend to just kind of work bursty. All right. I'll probably just start repeating myself at that point. But yeah, that's really all I had for today.
Thank you, Professor. That was helpful.
Yeah. But it's like I've probably given that talk 20. If I've been here 20 years, I've probably given it 40 times, because there's two senior, 198A starts every semester. So, but just, yeah, be honest up front about how you want to work, right?
Thank you, Professor.
Okay, any questions? Okay, well, anyway, I'll be more organized for next week so that we can have somebody come in and talk. I don't think he'll want to be recorded, but I'll try to promote it better. Okay. All right.
Thank you.
Take care,
Thank you.
guys.
See you next
Have a
week.
good day.
All right.